on the paper chair of many top conferences. He has published more than 50 papers in IEEE TVCG and IEEE Visualization Conference, the very top journal on the conference. And let's welcome Professor Shen.
Okay, good. Thank you so much, Guihua, for the introduction. So my name is Han-Wei Shen. I'm a professor at Ohio State University. Today is my great pleasure to share some of our recent research results on using machine learning for scientific visualization with you all. So this is because this is related to scientific visualization. So I want to talk a little bit about the general visualization pipeline that we are concerned. So basically, scientific visualization is mainly to deal with supercomputer simulations. As supercomputer become more and more powerful, as you know, the size of data become really big, right? So typically the process is, the simulation is going to produce a lot of data and then store in a disk, right? And most of the time, the data cannot be analyzing right away. So this is actually why we need to rely on post-analysis, i.e., after the simulation is done, then the scientists need to open the file, maybe using the front-end computer workstation and start analyzing and identify features. So like I say, typically the challenges is that the data are often very large, right? Nowadays, you can easily reach several tens of terabytes, 100 terabytes or beyond. And also the other challenge is that because of this, the size of data is so big, right? So, interactive exploration is often very difficult. However, a lot of time when they run simulation, the scientists, they do not know the exact location or the time of the feature that will appear, that will interest and also allow them to identify, the salient knowledge. So because you cannot do batch interactive exploration, you have to rely on batch mode processing, but then this will make the discovery of feature very difficult. So this is, the whole thing is about feature extraction, right? You want to identify a feature, you don't know where it is. Now, and also there's so many parameters you need to explore. For example, when it comes down to visualization algorithm, you need to, I say, for example, ISO surface, you need to try different ISO value. And when it's like a flow visualization, you want to extract streamline, you need to identify the seeds, right? You want to place the seeds and also trace the streamline over. Now, there's so many parameters you need to specify, and you need to identify the salient location, value, time, and so on and so forth, so that you're able to get information. So this has been a great challenge for the past many decades. Even though the research result has been produced by many people, but the simulation is now become bigger and bigger. So really the problem still remains. So now for the past 5 years, also the machine learning has become AI in particular, neural networks has become the mainstream for AI research. But approximately for the past 5 years, people in the visualization community start to look into how can we utilizing machine learning techniques to facilitate scientific visualization. Now, there has been many papers published in the past 3-4 years, and people have novel use of machine learning, in particular neural networks, to facilitate exploration. For example, it's something so-called latent representation created by autoencoder that will allow us to reduce the size of the data, but in the meantime, keep all the salient information from the data. And also to identify feature, can be considered as a classification problem, right? People do not necessarily have a rigorous mathematical definition for features, but however, if you are able to identify the data that define the feature, this is where the artificial intelligence can help you to find data that has similar pattern, and so that you're able to classify and extract features. At Ohio State, we have been also working on producing something we call that simulation surrogates. So what is that? Typically we know that it takes a long time for simulation to produce results, right? And this is really not our job. This is not visualization people's job. This is really scientists who perform, computational research, they are going to write simulations. However, typically simulation is running on supercomputer. It takes a lot of time. So, this loop, this cycle of producing data, analyzing data become really, really long. So in order to facilitate, say, parameter space search, right? So one thing that people can do is we are able to actually take the existing simulation result as a training data, and we are able to train something called surrogate. So surrogate is we actually skip completely the simulation based on the input parameters, based on the result that have been generated in the past. We are able to predict the result that could be generated from simulation. However, we are not running simulation. We are running through the surrogates. Actually, at Ohio State in the CSIG-VIS 2019, we had the best paper under the CSIG-VIS conference talking about how do we produce surrogates for parameter space exploration using an image-based approach. So this year, actually, yesterday, we had a paper presented in IEEE Pacific Visualization. My student Nan Shi talk about how we can generate this using GNN, graph neural network, to produce data for unstructured grid meshes. So the presentation was yesterday. But if you're interested, you can also look at the IEEE Pacific proceedings. And this was selected as one of the 5 papers to be published in special issue of IEEE Transactions on visualization and computer graphics. Now, so there's so many things. For example, without exhausting through all the possibility, people also apply machine learning for reconstruction, super resolutions, and then dimensionality reduction. And even people apply to rendering, with, like, for example, style transfer, and also some kind of interaction, visual design and layout that people have demonstrated that AI can be very, very helpful. So now, today I want to mention a subset of our papers published in this year and the last year. For example, I'm going to talk about how we actually using machine learning, in particular autoencoder, to represent particle data. Particle data has specific challenges. I will talk about it. And also, this is the next paper I want to describe today is a joint work with Guihua, Professor Guihua Shan, our session chair today, about how do we perform space-time super resolution for vector field visualization data. Now, because of time constraint, I probably won't be able to talk about the other 2 work, but if you're interested, you can find a paper. One is actually our very recent acceptance of the paper submitted to IEEE TVCG about how we can use reinforcement learning for particle tracing. So the focus of the research here is that when the data is so big, you need to distribute the workload, i.e. the streamline seed to different processors. Now, because the seeds are placed at different locations, they are going to travel through different regions of complexity. So very easily that different processor will have different workload. So this workload imbalance is going to cause slowdown of the computation. So now in this piece of work, we actually talk about how do you look at the complexity of the work? How do you look at past history of the particle tracing? We are able to do automatic load balancing using reinforcement learning technique. The final piece of the work here is GN surrogate. This is the Pacific-VIS paper I just talked about, published this year, and also presented a couple days ago, and about how do we use graph neural network for producing simulation surrogates. Now, so I'm going to spend most of my time today to cover the first 2 pieces of work. By the way, if you have any question, you can probably type your question in the chat window, and Guihua is going to collect the question. I will be able to answer. But feel free to type in your question. I'm going to answer your question in the end of the talk. So now let me describe the first piece. So this is, if you're interested in autoencoder, even though you might not be doing scientific visualization, you might find this work interesting. And also, if you're not working on scientific application, but you have interest in point cloud data, this piece of work might also interest you. So basically what we are trying to do is, you look at these images, this is actually a particle simulation data set generated. This is essentially, you can imagine this is like this CO2 pump from the top of the cylinder and then into the water, and then the CO2 is going to resolve with the water. It will create a lot of very complex geometric structures. So we call this viscous fingers. Now, viscous finger is an interface between two different fluid media. Here you can imagine it's the CO2 and the water. Now, because the interaction of the chemical reaction, they will form some kind of very specific shape. And there's a finger elongated structure, we call that viscous fingers. Now, this is one example of features scientists trying to extract. So the data produced by simulation is actually a lot. You can, of course, you can always produce, images by rendering each particle as a small spheres, right? But this will easily give you tens of millions of spheres. That's a lot of data to produce, to interact with. Now, so one goal of this work is we're trying to identify those features we call the viscous finger, that is elongated structure in the data, by considering the attributes. For example, the CO2 concentration and also the shape. So the shape is really related to the particle position, how they are distributed in space. Now, the advantage of feature extraction is that you are able to only focus on regions that are most likely being region of interest, being interesting to the scientists, right? So here I just list a few advantages of performing feature extraction. So first of all, you are able to understand and focus on particular scientific phenomena, right? Also, because once you identify where the features are, you can remove or throw away all the other data. So in this way, you are able to process probably a very small fraction of the data and focus on how and watching how the feature evolve. So this is actually way much more effective compared to you render the entire data set over time and then try to see what coming out of images. So if people have been doing feature extraction to reduce the load of data processing. And then finally, because this is three-dimensional data, typically we suffer from 3D occlusion, meaning you may not be able to see those something so-called viscous fingers if they are behind, if they are blocked by structure, unrelated structure in the front. So now, if you are able to extract the viscous fingers, you should be able to overcome by a large degree the 3D occlusion problem. So now, how do we, feature extraction in scientific visualization field is actually a very difficult problem. This is because a lot of time depends on the domains you are talking about, say, computational fluid dynamics or cosmology. The definition of features a lot depend on the domain people. Right, so now different domain sciences, they have their own definition of features, and oftentimes those features, they do not necessarily have specific mathematical definition. The scientists will know it's a feature when they see it. However, they might not be able to write down the equation and say, if your data are satisfying those equations, it's feature. This is oftentimes doesn't exist. Now, because you don't have a specific mathematical equation, right? You cannot simply plug the data into the equation to identify this is feature, this is not a feature. So what people do, people actually, just like a machine learning problem, you have to handcraft some feature descriptor, right? So you might, based on your domain experience or some sort of ad-hoc knowledge, you need to identify feature descriptor, and then using those feature descriptor, a combination of which to define the feature. But this is typically, we all know that this is called feature engineering, right? Feature engineering is actually non-trivial because you might not always be able to pick the right feature. This is where I want to introduce our work. Is we're hoping that we identify the most salient property from the data with a unsupervised training methodology. You're able to separate things that you consider feature from things that are not features, right? So this is going to be something that I want to focus on maybe in the next 20 to 30 minutes. So now, specifically, I want to talk about particle data. Now, as we know, AI techniques in the past have been very, very successful for image data. Image data are, regular structured grid, right? So, because they are regular structures, so you can actually apply convolutional kernel, 3x3x3 kernel, to process data, and then the image analysis people have shown that you can achieve great success to identify objects, and track features accordingly. However, for scientific application, particle data is actually a completely different animal. So by that, I mean, particle data, they are, pretty much scattered across, the domain, right? And then because they are particle data, you do not have a connectivity defined, right? So this will make analysis of the feature very difficult because you don't have a fixed structure. Given a particle, you do not necessarily know where the neighbors are. You need to search. And then because they don't define at the regular spacing points, it's impossible for you to apply things such as convolutions defined for images to identify features. So what people do typically, is when you get the particle data, they first of all resample into regular volume, based on density, right? Like, you can divide your space into n by n grid, for example, grid points, and then given a small cell, you count how many particles are within a cell, and then you record the density, and you convert a particle into a regular volume metric data. Then you perform volume rendering, isosurface, and so on and so forth. However, as people, you can guess, right? When you resample the particle data, you will have some region you don't have sufficient samples, and then in the meantime, you might have some other region you sample too much, right? So in a way, resampling data is always something that scientists who produce simulation do not want to see, because they don't want you to touch the data. You say, hey, I run this simulation based on some scientific principle. I don't really want you to resample my data. So this is one problem. So what I'm going to do today is that, given a time-dependent collection of particle, we don't want to resample the data. However, we want to be able to represent every sub-region of the particle by something we call a latent representation. Now, if you are familiar with neural network, you know that typically the latent representation can be produced by autoencoder, for example. Of course, there might be many other methods, but autoencoder being one of the methods that people use to extract latent representation. So what is latent representation? You can imagine is an information bottleneck. Given a large amount of data, you try to convert through a sequence of convolution, and then you try to constrain the dimensionality. In the meantime, that small reduced data can still capture the most essential information of the original particle or data groups. Now, for a given particle data, there are a couple of things important. One is the physical attribute is important. So here, the second bullet, because typically when scientists run particle, every particle you can consider as a point is going to capture a multiple physical attribute. For example, the density, the pressure, and every particle will move. It will also capture velocity and or momentum in different applications, right? But in the meantime, a group of particles, based on how they are spreading out in space, they also define something called geometry, right? So now, if you get 1 million particles spread out in space, now you might want to consider, how do you categorize every small neighborhood? That small neighborhood contains a particle spread out in particular shapes, but in the meantime, each particle carry a particular set of attributes. So the question now is, how can you have a most succinct representation for each particle that simultaneously describe the geometry, meaning how your neighbor, spread out around you. In the meantime, the attribute, not only the attribute of yourself, also the attribute that is associated with your neighbors. Now, so what is the benefit of this, right? Once you convert the, time sequence of particle data going through neural networks, which is a autoencoder type of neural network I will present it, then you reduce your large number of particles into a much more succinct set of latent vectors that describe either a single particle, a small neighborhood of particles. Now, with that latent vector, and actually in our TVCG paper we just published, we show that you are able actually to conduct feature tracking. Feature tracking of particle is not necessarily trivial because you do not know how many particles to include to define it as a feature. But now and also there are too many particles, too many attributes to look at it, right? So now we're able to actually consider for every particle, we'll consider local neighborhood that simultaneously capture the geometry and attribute information into a small dimensions represent as a vector. You're able to track the local neighborhood based on the latent vector, based on the similarity of your current location. When you go down to the next time step, you do a neighborhood search to see what particle or group particle carry the most similar latent vector, because latent vector is supposed to be very informative. Then you can move your window in space and time, then allow you to track the features. Now for this viscous finger, the animation I just showed, we are interested in tracking this finger, those tip of the feature that is the interface between CO2 and the water, for example. So in that paper, we actually talk about how do we use the latent representation combined with mean shift algorithm to match the latent distribution over space and time. Now, today I want to mainly focus on how do we actually compute the latent representation for a collection of particles. So I'm going to kind of convert this talk now. I transform into a more like a machine learning sort of a content. Basically, let me a very high level view. This is a autoencoder, but this is not like a traditional convolutional based autoencoder, because I want to remind you that we don't have a regular structure voxel for us to perform regular convolution. What we have a discrete set of points in space. Now, but let me tell the input output. So here you can see that is a encoder this is very typical. We have encoder, we condense the input information into a information bottleneck. We call that latent vector. And as a part of training, our goal is to taking the latent vector through the decoder and the reconstruct back to the original particle set. So if this is, we are able to successfully train that, then this middle latent vector is going to represent the information for a particle over here, the red particle, and also is a surrounding. So typically, when we design such a autoencoder, we assume you are going to input something called particle patches. A patch of a particle contain n particles, which include one particle in the center, which is the particle in question, plus n-1 nearest neighbors. All right. How do you identify nearest neighbor? You probably need to do some preprocessing. For example, you do KD partitioning. You divide the space into different spatial component, and then you do this recursive subdivision using so-called KD tree. You are able to identify the nearest neighbor. So we are assuming that this is given, meaning you are given a patch of particle with a 1 in the center and the other n-1 around it. We are going to input this particle into this autoencoder. So I have 3 boxes that I want you to get attention. So let me animate again. So now, because of the particle are not regular grid, we have to consider a different way to do convolution. Now here, we're actually borrowing a concept called geocom. So this is something not published by us, by some other people in the AI community. So this may be one thing hopefully you can learn today. So if you have point cloud data, you might consider to utilize geocom to extract feature for your own application. But the middle box is the latent vector, which is our key. Once we get latent vector, it's much reduced space with enough information. We are able to do a lot of things. Right, so I'm going to, hopefully you can at least learn one thing from today's talk is what is geocom, because we actually benefit from that geocom a lot to extract latent. So now I want to remind you that we actually, for the geocom component, we enter n particles into this encoder, that geocom plays an important role. Now, each of the n particle has a dimension 3 plus d. So let me explain why, because every particle has a XYZ location, right? So that's 3 dimensions. Now we assume the particle carry D attributes. So the dimensions of each particle, we can consider that as a feature vector. xq I represent here. Now I got n of them as input. So each xq here has 3 plus d dimensions. I got n of them. Now, let me kind of describe the high level idea of this convolution geometrically. This particle 3 plus d vector is going to be multiplied by 6 trainable matrix. Why 6? Because you can consider we are talking about 3-dimensional space. There is a x direction and also in the meantime minus x direction, right? And then we have y direction, you have a minus y direction, z direction, minus z direction. So essentially we are going to train, they are trainable matrix. We're going to train 6 different matrix to transform the 3 plus d vector for every particle into a representation of 64 dimensions, right? So you can imagine that each particle is 3 plus d dimensions, and then they are going to be multiplied by w, but we have 6 of them. Each of them is going to give you 6-dimension output. And then you can imagine that they are so-called feature vector. Now, because the training of the autoencoder is to recontour particle eventually, so this is learnable matrix for w. And then we are going, when you succeed your training, then the 64 dimensions of the vector become the most salient representation for each particle. All right. Now, but also eventually, because remember one thing is we want to come up with a single vector represent the particle patch, not n of 64 vector. So we have a another weighted sum and a neural network combination to reduce from n 64 dimension vector into a single vector code that has 256 dimensions. Now, I'm going to describe each individual step to you with a little more detail, but you can just imagine that by the end of this convolution, we get a single 256 dimension vector to represent the entire particle patch. And this is supposed to be the most salient information for the particle. All right. So now I'm going to describe, just to give you a little more idea how each step is doing, so such that you're able to hopefully appreciate the importance of or the effectiveness of geocomp. So now, so I gave you actually a high level idea, but I want to just probably remind you with a little more detail is now every particle has 3 plus d dimensions. Now they all share 6 matrix to decompose the information into 6 dimension. The x minus x, y minus y, z minus z, and this is trainable. All right. Now, when you are converting the 3 plus d into 6 vectors, then obviously, because I'm going to combine the 6 vector into a single 64. So what I'm going to do, I'm going to, based on once, so assuming there's a center particle P, but I'm talking about particle patch, right? So each particle in the patch Q has a vector in this diagram here, P to Q, right? I basically calculate a cosine distance of PQ to each of the 6 dimensions. That will be the weight used for me to perform a weighted sum for 6 different 64-dimension vectors. Now, so here, you can see that first of all, I convert this Q attribute of Q of particle into 6 feature vector. But now there are the feature vector corresponding to each dimension. So I perform a cosine distance calculation. Then I do a weighted sum. So you can see that at this stage, for every particle Q around particle P, based on the position offset and also the attributes, I'm able to combine that into a single 64-dimension vector to represent particle Q. All right, but you're going to remember this is only for one Q. For one particle, I have n minus 1 particle around P, so I'm going to have to combine it. But this is the, before I combine it, I want to represent as much information as possible. So I actually upscale for every particle from its own 64 dimension to 256 dimensions. So this is essentially upscale such that I'm able to allow more information to be represented by the particle. Okay, so now I'm hoping you are following me. If it's in the classroom, I'm able to actually answer questions, but I just want to remind you that because the particle patch has n-1 particle Q, and every particle has a 256 dimension or feature vector that carry the most salient information for that particle. However, given the particle patch, right, I still have n of those particles. Now here, what do I do is I'm going to try to combine it. So how do I combine? Think about it. For given a center particle, I got n-1 neighbors. So you can just imagine the way I combine it is based on the distance, right? If they are closer to the center particle, I will give more weight. If they are far away from the center particle, I will give less weight. So I basically calculate its weight based on distance. R is the radius of the maximum distance you can reach, you care. And P minus Q is how much that particle is away from the center particle. And I just do a linear ramp to decide weight, and I do a weighted sum. So now this is where I calculate particle. Eventually, I got a single 256 dimension vector to represent the entire particle patch. Okay, and this vector is very important in the sense that it will capture the position, direction from the center of the particle patch. In the meantime, it will also capture the physical attributes that is being captured, is being carried by the particle. So now, and also because I do this aggregation through the trainable neural network, then this 256 dimension vector is become the most salient information for the particle patches. All right. So now this is just a very quick view of the convolution for particles. So essentially, you can imagine that even though we don't have a regular structures, but I project particles of attribute into 6 regular dimensions: x minus plus, y minus plus, z minus plus. I'm able to perform simple aggregation just along those 6 dimensions. So I'm still able to get a convolution result. But of course, I want to remind you, if you look at backwards, this is actually geocount is only one component. Then we are going to go through the normal neural network, i.e. batch generalization, nonlinear function ReLU, and then fully connected, and so on and so forth. Eventually, as you come out to the middle part, this is a latent vector represent this particle patch that will capture both geometry and also attribute. Because remember, we do care about how the particle spatially distributed, because that typically defines the geometric features. In the meantime, the attributes. Okay, now, so let me talk a little bit about the trainings. So this is the key I just passed, but then training is something, for example, you have a lot of particle in your data set. How do you select them? So typically, given a large size data set, which we sample 1% of particle for training, right? And then each particle from that 1%, of course, carries 3 plus D, 3 being the spatial information, D being the attributes. Now, one thing we want to remember is because the many particles may be boring. Okay, so they may not be able to carry the salient information for successful training. So we actually try to reverse it. So the chart on the left is actually the distribution of particle. You can see that you probably don't need to worry too much about what x-axis is, but you can imagine this the value, the y is the frequencies. We actually try to sample as many particles from not so frequent group as possible, such that our network is able to capture not only the most common particle, which are typically background, which is boring. For scientific data, the scientists is much more value, they much more value the uncommon particle. So we actually increase the frequency for a particle that are not common. So now the chart on the right are the sampling frequency from the particle that among that 1%. So you can imagine that something that had low frequency, we actually make those particles, we sample those particles more. Okay, now, so let me quickly talk about how we utilize it. So now once you have a particle, a patch of particle, once you represent the particle by 256 dimension vector, you are able to, so here, for example, if you look at the chart, the diagram on the right, we just perform t-SNE projection, right? And based on the latent representation, each latent representation is a 256 vector, you can perform clustering. So now image on the left is our hierarchical clustering result. Now, even if you don't look at the hierarchical tree, you look at the image on the right, you can see that there are clear several clusters. They actually represent different regions in our particle data. So basically, once we create a particle latent representation, which contain a collection of particles as a patch, and using a succinct 256 numbers to represent it, you're able to do hierarchical clustering. Then this is just a tree of hierarchical result. Then actually the scientist is able to choose different nodes in the hierarchical cluster tree, and then look at how they are in the t-SNE space. And then furthermore, we are able to map to a spatial particle visualization window to see where they are. All right, so now this is just one thing that once you get latent representation, you throw away non-important information, you're able to see the feature space much more clearly. If you simply project, you might ask me, say, why don't you just project 3+D particle as a point and store entire data set into this t-SNE space? Things is because each particle is 3+D dimension, carry too much redundant information and noise, and chances you're not able to see the succinct information on the t-SNE projection. So the important thing is in order for you to get a clear structure of the particle in the feature space, you want to throw away unimportant information. And this is actually what we discovered, that with this geocon and also plus other neural network, you're able to get the most salient vectors retained. Now, so this image here, I just want to say that with the hierarchical tree, with you selecting different nodes, we are able to separate the particle data. This is the viscous finger data into different groups. Then we actually color the groups into different, we actually, display the different groups. They have a distinct feature collection in the feature space with different color. And you can see that they are actually spatially split. And also if you look at their value, they actually represent different attributes in different range. Now, we're trying to compare with topological analysis, which is the image on the right. In this case, what people do is actually, this is one of the winner for the past CSIG-VIS contest. What they do is they given the particle data, they resample into volumetric density, and they do isosurface. And we can see that, we actually show a very similar structure as isosurface. However, we're able to separate the feature much more clearly. Here, they all connect together, right? So if you don't know what you're looking at, sometimes it's hard for you to identify the features. Now, what I want to show here is we do a comparison. So the image on the very right is actually our method. As you can see that we're able to separate those because we want to find those finger structure, elongate the tips. We are able to separate them by using the feature vector. But if you look at the two images on the left, this is like a thresholding. You look at the particle and you stretch by the value, but you can see that they either all cluttered together, so you're not able to separate individual fingers, or you miss. If you look at the image at the bottom, you're using different threshold. Some finger here, you can see that it's missing here. So this is actually the advantage of using much more succinct latent representation. And then this is just an example of another data set, the supernova cosmology simulation. The image on the left is original data, but because we are able to extract the salient information for the latent, we're able to separate foreground, all right, which is yellow, from the background, which is blue, right? If you look at the original data, you do not really know foreground, background. And we can even further, if you go down to the hierarchical clustering result, we're able to separate even more, like orange, like yellow. You're able to separate the different structure, as you can see, because they distributed space. Spatially, they actually mean something that is distinct in the spatial domain. Okay, now this is just a quick image. I don't have an animation, but if you can see this small box with the particle patch feature descriptor and combined with our mean shift algorithm, we are able to track the feature. The top is the tracking result. This is our small window that we track. So we can track the finger because the finger will change over time. We are able to track very precisely. But if you look at down to below, the blue arrow point to something that is tracked using particle value directly, and we actually realized that very quickly that track window lose the features, right? But now if we use a succinct statistical representation of our feature vector, we are able to track much longer period of time. Okay, so this is actually the end of my first piece of talk. I hope you all appreciate the power of using machine learning technique, specifically using autoencoder combined with particle-based projection. We're able to extract a succinct representation for patchwork particle, right? And then from that, you're able to perform exploration, you're able to perform tracking and other things, much more easy to identify spatially and also physically salient information. All right, so now I want to move on to the next piece of work. This is actually a collaboration with Guihua. The first author is Guihua's student, and Guihua, Han-Wei visit Ohio State a couple of years ago. Well, unfortunately, during the COVID pandemic, so when she came, mostly she's hiding because our school was shut down, everything. But she was able to produce something I consider very good in terms of time-dependent flow visualization, super resolution reconstruction. So let me describe, but of course, this is really a lot of work is coming from Guihua and Yifei and the Li Guan, which is also in Zhonghe Yuan and the Liu Jun. So if you're interested, you're welcome to contact them. They probably will be able to give you more information. But let me give you the gist of the work. So I want to remind you, this is the piece is something we don't overcome, right? The data is too big, right? Produced from the numerical simulation. Now, really, scientists want to reduce the amount of data they have to save, right? So you can imagine, why don't we do downsampling space and the time? But the problem is they want to be able to do a high quality analysis in the post hoc stage, right? So throw away data is not really something the scientist is going to trust you to do. So now what we're trying to do is actually, so this is just same old issues. I don't want to repeat myself. What we're trying to do is that possible that we throw away as much as possible during the simulation to the disk, right? However, before you want to do post-hoc analysis, we want to do super resolution, meaning can you reconstruct higher quality data from low resolution data you saved? So this is, sorry, I forget it. Okay. So I want to tell you the idea of this paper. This paper was published in last year's special issue in IEEE Computer Graphic Application. So the following is the idea. So this is the original data produced by the simulation, but we are not able to store all of them. We cannot afford to. It takes too much space. So what do we do? First of all, we do a spatial downsampling. All right, meaning, for example, for every time step from I to I plus k, okay, k could be a large number. I reduce each of the time step by 2 by 2 by 2, 8 times, right? Spatial downsampling retain the most salient information, but you lose some kind of features. But now we want to do even further downsample in time, meaning, for example, instead of keeping every time step between I and I plus k, I only keep the time step I and I plus k. I only keep 2 time steps. Now, this is what we are going to store. But of course, in order for you to perform a high quality ad hoc analysis, you want to be able to reproduce higher quality data from the limited amount of data you store. Now, what do? We're hoping that during the data we want to train a neural network. So once the neural network is trained, you only need to give this, you save this to disk, then you show it all the data you have. All right. And now, this is where you want to perform super resolution. That is, once you have model, you take the first and the last time step with reduced spatial resolution. You want to be able to reproduce higher quality. So what we do is the neural network model I'm going to quickly introduce is to upsample. So actually, this is the type of upsample to a higher temporal resolution. But because the size stays small, which is, I just want to try to visually indicate that they are still low resolution. But then the first step of reconstruction for neural network model we train is to upsample time. Then we're going to upsample spatial domain. So this is spatial domain super resolution. Then eventually you get this top row, high resolution, high quality time varying data, and you can perform all kind of analysis. So I'm going to describe quickly how the network is constructed, right? And then we can perform analysis. So this is a problem statement in a more formal way. We are trying to train a neural network to learn the function f, which take two time steps, the first time step, last time at the low resolution as the input. But we want to be able to produce a sequence of the data between I and I plus k at a high resolution, right? So now, that, like I say just now, we actually divide the reconstruction into two stages. One stage is you want to perform a temporal super resolution, meaning you get the first time step and last time step low resolution data. You want to produce a sequence of data in between, still at low resolution, just for now. The second stage, you want to perform spatial super resolution, which means you want to bump up the resolution of the spatial for VI all the way to VI plus K up to high resolution between VI and I plus K. Okay, so now let me tell you the construction of neural network. A lot of detail probably depends on, you need to read the paper, and then maybe you're welcome to talk to me or talk to Guihua afterwards. Now, so I'm going to talk about first of all, how do you perform temporal super resolution, i.e. taking a bunch of the first time step and last time step, how do you create the time step in between? So this is actually based on, we want to identify something called, we want to estimate the motion, because you can imagine as a time step 1, your vector go to time step 2 vector to 3 vector, there is a motion that push the vector to different locations. So you can imagine this is optical flow. So we want to do the motion estimate. Once you have motion estimate, you're able to warp the data into the new position. Now, this is actually roughly the motion estimation plus fusion. The fusion is because you want to calculate from the first time step to the time step in question, the last time to the time step in question, and you combine it. So this is a temporal super resolution. Once the temporal super resolution is done, you get a sequence of intermediate time steps at the low resolution, then we perform spatial super resolution. All right. So now let me give you a little more detail. This is a formal description of what we do. We only have the first time step and the last time step. We want to reconstruct the time step in between. And how do we do that? We are going to base on motion estimate during the training network of every time step, how the time step of data is moved the next time step. So once you successfully train the neural network, given the first and last time step, given any time step in between, you're able to look at these two equations. I'm able to reconstruct the data for the intermediate time step based on the motion estimate to move the first time step and the last time backward and forward into the intermediate time step. So this is one thing. The f of t here is the motion field you try to train by the neural network. But of course, inevitably you will have an error, right? You have error of this warping of the vector based on the motion estimate from the ground truth. And what do? You want to find out the residual. So again, the neural network is going to also train the residual such that you have a warp of the vector data plus the residual. Altogether, you're hoping to, to arrive at the final vector field as close as possible. Now, the fusion part is, like I say, you actually can predict the forward from the first time step to the time step t you're interested in. You can also predict backwards from the last time step to the front, and then you're going to have two different prediction. So now what you do is you just fuse them together to find out a final time step, final result for the intermediate time step t you want to find out. Okay, so now I guess I'm not going to go to very detailed, but essentially you can follow the red box. Actually, you can see some Chinese here. So there's a motion estimate, right? Like I say, the goal is to have a network. We use UNet to learn the motion optical field such that you're able to, from a 2 n time step based on the time step you're interested in, you can actually completely repeat and learn the motion field and then reconstruct the time step of the vector data at the time step I. Now, then you are going to, based on the motion field, you are going to warp the first and last time step into the time step t, which is something that you are interested in. But you're also going to train, for example, if the time step is closer to the first time step is going to have more weight. If the time step you try to predict is close to the last time step, then the last time have more weight. So you want to train the neural network to learn the weight. such that you are going to combine them together into the intermediate time step at time step t you want to predict. All right. So now this is, of course, I don't think I'll give you sufficient detail, but this essentially we are utilizing UNet. We're trying to learn the motion field. We try to predict forward and backward, and we combine together. More detail you can probably find from the paper. Now, at this point, what we have done is we produce a sequence of intermediate time step at the lower spatial resolution. So the next step in our work is you want to bring up the resolution. Now, there's a lot of detail here, but I want to give you a high level concept is, important concept here I want to introduce is we don't just upsample from every single time step without looking at your neighboring time step. This is because if you only do super resolution, there are plenty of work that can do super resolution from lower to high res. However, given a time sequence, if you only perform the spatial super resolution individual time step without looking at your neighbor, you are going to get this so-called popping effect. When you animate, every time step is reproduced to some similarly good quality. However, when you run the animation, you're gonna have noises, show up, disappear. So when you look at the animation, it becomes very, very annoying. All right. So now, we actually propose something that we use something called deformable convolution neural network. That this is a time step here. This VJLR is a time step you're trying to bring up to high resolution. So that is what super resolution is going to do. However, we are going to look at the neighboring. So I only draw one frame, but you can see all the neighbor frame. Other frame, you want to combine the feature map together before you do super resolution for time step J. So here, from the top to down, we actually repeatedly bring down the resolution for the feature map to 3 different scales, just as example, and you concatenate together with the current time step. Now here we're trying to do something deformable convolution. So this, give you a high level idea is essentially we all know convolution is to apply a 3x3x3 kernel, for example, for 3D and 2D 3x3 kernel, but this will limit amount of information you can fetch from your neighborhood. So I think deformable convolution network is a paper written by Microsoft Asia, I believe in Beijing. What they say is instead of having a fixed 3x3 around the center pixel, you actually add offset such that you collect 3x3 pixel from far away, and how much you want to collect is trainable. The offset, which the offset is trainable. So now, without giving you too much detail, is once for every time step you combine the feature map from your adjacent time step, then you perform upsampling convolution. But this upsampling convolution is done through deformable convolution neural networks. This allows you to fetch information from farther away, and then once you align it, you get a feature map. And then now you can do this usual thing, right? You do pixel shuffling, and then upsampling, and then based on the loss value, you do backpropagation, and you repeat training again, and to get a good spatial super resolution. So now, so this is the high level idea. I'm hoping you will get it. Now, as usual, once you train this combined neural network with the spatial and temporal, the goal is to approximate the result VT head back to the VT ground truth, which is GT. Then for vector data, you really need to have multiple loss function. For example, you want to make sure your magnitude, you're able to do a good job reconstructing. You want to make sure the direction can be done by cosine distance. All right. And then also a lot of time, given the velocity field, you also want to make sure the gradient field is the same. So this is so-called Jacobian matrix, and you want to calculate Jacobian loss. And then also temporal loss is, you want to look at the time, you want to average the time before and after to making sure the loss is minimal. So those are the loss function we use to train our neural network. And eventually you're gonna have to combine loss value together into a final loss before you can do backpropagation. Right. So now, let me move on to some quick results. All right. This is just basically, it's so far, I think one I'm going to mention in the future work is the training is still computationally very expensive. And I believe personally, this is what stopped machine learning to be used broadly by scientific application. Like for example, in our model development, for this 126 by 120 by 512 example, the solar plume data set, it took us 15 hours to train. All right. So when you got a Red Sea data, I believe this is earlier CSIG-VIS context data, and it takes more than 1 day, but this is the cost I think now that everybody has to pay if you want to use neural network approach. Right now, however, this one I'm trying to compare, using 2 data sets. So we are comparing our method, which is the rightmost column, with a bilinear interpolation, which is the leftmost column, and also I think there is a related work that they use LSTM plus CNN to perform super resolution. And then here we are random render for every point. Once we construct the vector, we compare with the ground truth, we get a magnitude of difference, and we perform one rendering. And as you can see that with our motion compensation and also spatial and the temporal super resolution, I hope you can see that our error is much less than a simple bilinear interpolation and also or ST and CNN. Now, this is just a qualitative comparison in terms of the tracing the path line. So the very left column is, you can see there's something I circled is one path line calculated, and you can see the middle 2 method, which is bilinear interpolation and STN. They don't actually over here, they don't do such a good job. But here, if you compare our method at the very right figure, you can see the path line is still being preserved reasonably well. Now, maybe you wonder PSNR, you might say, because sometimes people say, why do you do super resolution? So you can say one reason to do super resolution is to reduce data. Then people immediately say, then why don't you do compression? Right? So here, so if you focus on the leftmost column, we're trying to compare the quality, right? So SC is a lossy compression scheme, which is widely used by scientific community. Now, in order to perform fair comparison, we try to fix the compression rate, right? For solar plume, I think this is the compression rate, so that at least SZ and our method plus gzip, because once you convert the data into low resolution, you can still gzip, right? There's no reason you don't do that. But then we try to see, given such compression rate, if I use that data to render, right? S is lossy. Our method is also lossy, but you can see the PSNR, the peak signal rate noise ratio, our is at about 36 for solar plume, which is nowadays acceptable level. 35 and above is acceptable, but the SE, because it's lossy and because we force the SE to compress this much to be the same as our method, the PSNR is much lower. 14 typically is not acceptable. This just means you lose too much information from the data. All right, and then I guess this one just to show, because we are using our temporal super resolution utilized motion estimate, right? So you might wonder the motion estimate from our synthetic, our Rixona data versus the ground truth data, are they similar? So as you can see, qualitatively, the motion field computed from the ground truth data and from our reconstruct data, meaning the inference data using our model, are very, very similar. Okay, so anyway, so this is pretty much, so I'm almost at the hour time. So this is the second piece of work I want to highlight, is the collaboration with Zhonghe Yuan and under Guihua's supervision, and how do you perform spatial temporal super resolution or data reduction, if you wish, for vector field data. Now, let me give you my conclusion. So I firmly believe that machine learning is going to play an important role in scientific data analysis and visualization for the years to come. Because like in the very beginning, I say the machine learning can be used to extract set information as a latent. The machine learning method can be used for classification and segmentation. And machine learning method can be used for data reduction. Machine learning method can be used for simulation surrogate, which we have paper just this week in CSIG-VIS, and also a CSIG-VIS best paper in 2019. So I believe it has a full potential. All right. Now, of course, my last bullet I want to say is I don't see that it's quite ready yet. It's because of the amount of time to train a good capable neural model is still very long, and then and also I think everybody agree if you're working on machine learning, there's a lot of parameter you need to tune. So this parameter tuning thing become a big burden for every single AI model developer, right? Because if you don't spend sufficient time to tune your model, you might be performed very differently, right? So I think this uncertainty and instability still make sometimes the scientists not so trust the machine learning model. However, now almost a majority of students in my group, we are trying to develop different neural net model for different purposes in the pipeline of scientific data analysis and visualization. I personally believe, as our machine become more powerful, as we collect more data, so we have computation, we have data that will only make our model more intelligent. And I believe this is going to play a major role in pushing the envelope of scientific data analysis and visualization. And that concludes my talk. This is actually a picture of my group before COVID. So after COVID, it's so difficult to get together and train and take a group photo, but we are hoping that this COVID is going to go away from the world entirely. I know for the past few weeks in China, in particular Shanghai, has been very bad. So I really have give my best wish to people in Shanghai. And that's it. Thank you so much. Guihua, back to you.
Thanks for Professor's wonderful talk. And yes, AI opens a new channel to solve the visualization problem, where how to make good use of AI for scientific visualization is full of challenges. Professor Shen's team has done many interesting work. And I think it's time for question session. And there seems some problem in living room. So there are many professors and students in the Zoom meeting room. So I think the people in the Zoom room can ask the question directly from the meeting room.
I see actually in the chat window for the Zoom, because I only have access to Zoom, I see actually Li Guan asked 3 questions, right? I can try to answer. So his question number 1 is it feasible to explore the temporal change of structure, which is composed by particle in the latent space? For example, time series cross analysis. So actually, yeah, so I think this is actually what we try to do. Now, like when I mentioned this mean shift algorithm, we actually try to come up with the latent representation for each of particle patches, and then we try to track. So based on the similarity in space over time, we try to explore the temporal changes. So I would say it is feasible, but of course I want to say in our work, when we calculate latent, we do this 1 time step at a time. So we are actually not we are not doing 4D latent representation. All right, so this may inevitably introduce some kind of unwanted noise or discontinuity in over time. So I actually, and I think this is Li Guan, right? So I think perhaps we can consider whether it's possible to perform 4-dimensional latent representation with a small window. This might give you a smoother tracking trajectory over time. So I hope that answers your questions. So the number 2 question Li Guan has is that can particle map to latent space to obtain high compression rate? So I want to say this. So actually, this is a very good question, Li Guan. So far, the compression rate depends on how many patches you sample from your data. So if the patch, so patches is a collection of particles, right? So in a way, when you divide, you have to first of all divide your particle into groups, and for every group you do latent space. So clearly, if you only divide the data into big patches, you get good compression rate. But you might have thought that, hey, then you lose too much feature, because after all, a patch or a big collection particle produce one single vector, you may not have a good quality. So actually the number 2 is something we are still investigating, because my student told me that so far, this is actually why in the first piece of work, I did not highlight the compression rate, because my student told me that in order to get a stable result of tracking particle patches, he need to have a pretty dense collection of particle patches. So I want to say the number 2 is actually something to be investigated. I want to say right now, we are not so satisfied with compression rate for the particle latent representation yet, but I'm hoping that we can all work together to look into these features, these issues. Number 3, if we do interpolation in latent space, is it superior than direct particle interpolation? We actually have not done latent representation, latent interpolation. So again, like I say, right now we do is per patch, we extract particle latent representation, and we use that to do other things. Now, interpolated latent is actually non-trivial, as you see, right? For example, typically people need to, instead of doing autoencoder represent, you have to do the genetic model, right? Such as your sample the latent, right? Instead of interpolating, this is one reason people use VAE, right? To sample the latent from a TGB instead of directly interpolating latent. So we have not done this yet, but I think Li Guan, this is really very good question. Can you improve our latent representation such that you can interpolate directly without having more sophisticated particle latent model, which we don't have? Then you can achieve good goals. So I think we have not done it. So, but I think this is a very promising research direction. So I hope I answer your question, Guan. Okay, thank you.
Thanks for Professor Shen. And there are,
I think there's another question, right?
for you. Yeah, another question. Is it feasible to use machine learning to predict particle time series future before features appear?
Yeah. I think this is a promising future work, because like I say, right, our current work, we do this one time at a time. We are now introducing things such as LCTN to do prediction, right? Even though the second work somehow allude to doing a prediction based on motion estimation. So I want to say that I believe it's feasible, because people using machine learning model, to do temporal prediction a lot. So we have not done that, but I actually encourage you guys to look into how to perform prediction, because a lot of prediction is something that people consider very, very valuable, and I believe it's feasible, but we have not done it. So hopefully you can do it.
Oh, yeah. There another question is that for the work 2, the STSR prediction from beginning and from end. So how the mid quality?
Yeah, so actually, if you look at the paper, I believe we have this. So I maybe this is what you think. So basically, as you can see, right, if you do a quality chart, what we found out is the beginning quality is good, end quality is good. The middle quality is going to be relatively lower. Why? Because the middle time step is away from the first and the last, right? So maybe this is something you have in mind, Yihan. But overall, when we do a quality estimation, we actually consider, all the time steps. So that having that say, it means even the middle quality is satisfactory. But if you look at the quality chart, indeed, the middle time step is having a relatively speaking lower quality. And then how to improve it? Well, if you unsatisfied the middle quality, you probably need to shrink that, because remember when we do prediction, we have I and I plus K. So a brute force way to improve the quality is to reduce the K. But of course we know that if you reduce K to something too small, then you lose the point of doing reduction, right? So this is a parameter that we actually need to look into and need to tune. All right.
And there another question for the second work. What if we unsample the space first and then in time, in the time? So why you first time and space, how about just the space and the time?
So I think what we do, the reason we do is we actually go backwards, right? So especially, so in our reduction, we have a sequence of data, right? We don't want to throw away individual time step yet. So we actually reduce the data from raw data to same number of time steps at the low resolution. And then from that, we actually go down to temporal, removing the intermediate time steps. So the reason we do that, I think maybe Guihua, you can actually help me. The reason we do this reversely, right? Because we actually downsample in space because we don't want to throw away too much information yet. Then we downsample in time, and when we do reconstruction, we actually or resampling, we actually do reverse. But now we have not tried the reverse direction, because if you do time and space, you have to throw away in the middle one, right? Then you might lose too much information. So that's why we choose to do for this current framework. But I see a lot of other related research that actually, they always mix matches space and time, subsample and downsample. So I want to say that's the possibility, although we have not done that yet. So, but I think this is good. This is a good idea. You might want to think, how can you reverse the training and reverse the model a little bit to see whether you can get comparable results. Thank you, Xiaofan. Any other questions? I think you guys asked very many good questions, so I kind of feel I'm not answering any of them. But this is because all of you guys propose a worthy and new research direction. I'm hoping that you guys can actually, investigate it, and hopefully you will generate something that is even better.
I think there also have several minutes left. So I have the question about your listed on your talk, the fourth work, the unstructured measure ocean simulations. Could you just say some words about this work?
Oh, the last piece of work?
Yeah, the last work. You have mentioned in your talk later.
Right. So Guihua, you want to know more about that?
Yeah.
Oh, so unfortunately, I don't have a slides prepared, but this is actually my student Shen's work. So I can give you a high level view, but you can actually, I believe CSIG-VIS, they have this recorded video, right? If you're interested.
Okay.
But basically, so we are dealing with the ocean model. So in our 2019 paper, CSIG-VIS best paper, we are actually trying to do surrogate, meaning the simulation is going to produce data once you supply input parameters. But our 2019 paper is that you don't need to run simulation. You give me input parameter, we are going to predict the images. Now, so in the 2019 paper, we are assuming your data is image data, right? That is, the image are generated from one rendering algorithm and so on and so forth. Now, in this year's paper, we actually remove that constraint. We are actually trying to predict the data, and we are actually also assume your computational grid is not regular. So this is actually why we use GNN, the graph neural network, because we are actually trying to solve the simulation data production based on irregular grid. So now, because it's an irregular grid, you cannot use CNN anymore, right? So then we use GNN. So so the goal is very much the same. We are allowing the scientists to input a simulation parameter, and we use our GNN-based neural network to predict the three-dimensional data, which is actually similar to our 2019, except in 2019, we have a lot of constraints. It has to be image data. The image has to be pre-processed and produced from the visualization, from the simulation data. So in this paper, we totally remove those constraints, and we can handle object-based data prediction, and also we can handle irregular grid. So that's the gist of the paper. And then if you're interested, please discuss with us after you read Nan's paper. And by the way, Nan is he came here from Zhejiang University. He was a Tao Yubo Professor Tao student. He's an excellent student. Right. Thank you.
Okay, look forward for this wonderful work. I just want to discuss one more thing that, I know you were focused on the AI for science, but there are also some research were working on science, AI for science, AI for VIS, and there's many research were working on VIS for AI. So, but there often there were asked her questions that they have to train a good model to do the focused VIS for AI. So from your work, you have a good model. So do you ever think that you can also work for the VIS for AI to make more efficient to for your model?
So I guess what you're saying that because like for example today, right? I talk about AI for this, right? Using autoencoder, using CNN, using deformable, right? But then a lot of time the model is we develop the use for this, right? But then if the model is no good, then our result is no good, right? So clearly we need to be able to analyze the model, because actually one of the students here, the one by me, Junpeng, has done a lot of work in terms of VIS for AI. GN VIS. Yes, actually I talked to my student, I say, hey, instead of working on machine learning model, why don't we work on our own model? So this become VIS, VIS for AI for VIS, right? But so you can imagine you can combine those things, right? VIS for AI for VIS for AI for VIS, right? You can do arbitrary, right? So in a way, it's a VIS for AI for VIS, like a square or cube, right? We have not done that in terms of writing a paper, but I always encourage my students, say, when you have a doubt in the model performance, you should apply visualization to analyze the model. So to some extent, my students are doing that, but we have not come to a point, being able to write a paper. I know, like for example, Li Guan, Guihua, your staff, he's working on like in situ analysis of AI model. That's in a way sort of hopefully can come back to facilitate in situ visualization. So I think that's a promising area. It's probably more like benefiting ourselves. So whether it's easy to write a paper, so you can imagine, right? So when you write a paper about developing autoencoder for particle, you might want to add a section about how do you visualize your own autoencoder, right? So that will make your paper much more robust, more rigorous. So I think that's a very, very worthy and important direction.
Okay. It's 20 past 10. So it's time we have to end here. And thanks again for Professor the wonderful talk. And thank all of you for investing your time with us. Welcome to the next international lecture on April 21st, where Professor Tony from Northeast University will give a lecture about visualization in data conversation. So let's meet in the next Thursday for the next wonderfulness. Thanks. Bye-bye.
Bye. Thank you, everybody. Bye.
Thanks, Professor Shen.
Thank you, Guihua. Talk to you later. Bye.